Uh, we'll see when we finish. It might not be the full like 20 minutes after, but we'll see what we can get through. So I'm going to start with this screen share. And so I'm going to try to do my best to get through material. Last week, or the last 2 weeks, we were talking about Python functions. And so let me actually pull up those slides right here. So we talked about how to write functions. There's the different parts. So this is the review from last week. Every single function starts with def, then you have the function name, and then you have the function parameters. Inside the body of the function, it's really just like any normal code. So the body of the function wasn't really anything too new. The only thing that we talked about for the body of the function was this return statement. And so the return statement basically turns this function into providing a value after it's run. So the function executes, all the code inside the body is run. And then if you have a return statement, after everything finishes, it gives you a value at the end. It's kind of like an output. Not all functions have to have a return statement. It's completely optional. You can very easily have a function that only prints out messages, or it only does some sort of computation, but doesn't need to pass it on to anyone else. The return is optional. And I think we've seen this in some of our homework. The most important thing is just remembering this first line. I like to think of it as like a template. This tells you how to use this function. A function is just like a tool that you build and then you use later on. So when you have a problem and you want to write a function to solve it, you really have to think, hey, how many inputs am I going to have? Depending on how many inputs, you have to make sure you have the right number of arguments here, right? Because you control it. When you're writing the function, you get to decide how many inputs does this take? 0, 1, 2. We even showed you how to do an arbitrary number of them. We also showed you how to do default values when you don't want to specify input all the time. You can just leave it as optional by providing a default value. And then we also talked about dictionaries. That was a little bit of a side lesson. Dictionaries were just like a data structure, kind of like a list, but the difference is that a dictionary provides a mapping from one data type to another data type. So you can have a mapping from strings to numbers. I give you a string, you give me a number. Like a real world example of a dictionary is a dictionary, but also like a phone book, right? A phone book is a classic example of a dictionary because you have names that you look up, and when you look up a name, you get a phone number, right? So you use one thing to get another, right? That's the whole idea of a dictionary. And they're pretty easy to use. Accessing, modifying, adding, all use the same syntax. It's all using the square brackets. So you have your dictionary, you have your square brackets, and then you put your key. And if it's a key that doesn't exist, then you're adding to the dictionary. If it's a key that's already there, then you're modifying. And if you don't do any assignment, that's looking up. So the syntax is all the same for those 3 different operations. The thing I want to get to today is really the last thing that we're going to talk specifically about functions. It's more of like actually supplemental material. It's not going to be really relevant to the things in the remaining 4 classes, although it is a very useful topic and is a nice way of solving a certain type of problem. And so what that new idea is the idea of recursion. And so this is a more advanced topic about functions. It's not just a programming concept, it's also seen a lot in math. The whole idea of recursion is breaking down a larger problem into smaller pieces. But it's not just any old smaller pieces. It's like a big problem that has the same structure contained inside of it. So if you can solve a smaller, easier problem, then solving the larger one becomes a lot easier. And I'll give some examples of that. Well, actually, I was kind of writing some up. I'm gonna redo this. But one example is the factorial function in math. So maybe in chat or speak up, has anyone heard of the factorial function? So like when I write 5 exclamation mark, does anyone know what that means? Okay, Derek, do you want to explain what this means?
5 times all the positive integers below it.
Yeah, so that's kind of a fancy explanation for it, but that's exactly right. So this exclamation mark is called a factorial. And what it means is you take this number, 5 in this case, and you multiply it with all the numbers less than it, and all the whole numbers less than it, down to 1. So 5 factorial is going to be 5 times 4 times 3 times 2 times 1, right? I believe this is like 120 or something like that, but not super important. But that's what 5 factorial is. And if we look at maybe 4 factorial really quickly, this is just going to be the same pattern, 4 times 3 times 2 times 1. Right? You take 4, you multiply it with all the numbers less than it, up until you reach 1. And so if I just told you right now to compute the factorial of some number and to use Python to compute it, can anyone tell me how they might approach this? This is definitely something that you could do right now with a tool that we learned kind of at the end of Python 1 and the beginning of Python 2. Yeah, so I see in chat, thank you, Derek, a for loop. Yeah, this is something that you could definitely solve using a for loop, or you could also use a while loop. Any sort of loop would work. But this idea of multiplying a bunch of things together, you could very easily come up with a for loop that does this. For example, like for all the numbers from 1 to 5, you just have some sort of variable that stores a temporary result, and you just add each number or multiply each number with that temporary result. And you just accumulate, accumulate, accumulate. And when you're done, you have your answer. And so you can definitely do this with a loop. But there's also another way of computing this factorial function. And it comes from really looking at the structure of the problem and seeing a pattern. And this is where recursion always starts. You have to figure out some sort of pattern to the problem. And maybe you've already seen it, maybe you haven't. But if we look at this very carefully, you'll notice that when we look at 5 factorial, right? If you look at this problem, let me use a different color maybe. Within 5 factorial, let's look at these terms. And if you look at this, you might notice that this is just 4 factorial. In other words, we can write 5 factorial as just 5 times 4 factorial, right? And so this breaks down our big problem, solving 5 factorial, down to a slightly smaller problem. Because the idea is if we know what 4 factorial is, then we can very immediately calculate 5 factorial. You just multiply by 5. And you can take this pattern again and again. So if we look at 4 factorial, what is this? Well, this is just 4 times 3 factorial, right? And so 4 factorial is just not 3, it's 4 times 3 factorial. And if you continue this pattern, you might guess that 3 factorial is 3 times 2 times 1 is just going to be 3 times 2 factorial. And if you look at 2 factorial, by definition, this is just 2 times 1. And it's also 2 times 1 factorial. And this brings us to the other important thing of recursion. All these sort of problems have some sort of what's called a base case, has some sort of like rock bottom solution the very most simplest case. In terms of the factorial, we can call the base case 1 factorial. Because if you use the definition of a factorial, it's a number multiplied by all the numbers less than it, all the integers. Well, 1, there is nothing less than 1 greater than 0. That's an integer. So 1 factorial is just 1 by itself, right? You don't have to do any sort of computation, right? And so if someone asks you, what is 1 factorial? You know the answer immediately. It's just 1, right? If someone asks you a different number factorial, for example, 3 factorial, you might not know the answer immediately, but you know kind of a formula to get to it. You know it's 3 times 2 factorial. And maybe you don't know what 2 factorial is, but you have a formula for that, 2 times 1 factorial. And then 1 factorial, you know the answer. So the whole idea is you break down this big problem, 5 factorial. You can break that into 5 times 4 factorial. You can break 4 factorial into 4 times 3 factorial, 3 factorial into 3 times 2 factorial. You bring it down, down, down until you reach your base case. And that's the whole idea of what recursion is. So we haven't reached the programming part yet, but this is the idea of a recursive problem. Another very famous one that we're going to get to maybe in class, maybe for homework, is the Fibonacci sequence. And so I'm going to talk a little bit more about that later, but that's something that you might have heard as well. Other problems oftentimes can be broken into this recursive structure. And in fact, I'm not going to prove this, but it's actually true that anything that you can do with loops, you can also solve with recursion. So looping and recursion are really kind of related to each other. They're equally powerful. So it's not like recursion gives you more power to solve harder problems. Instead, recursion can oftentimes give you an easier way of approaching the problem. Maybe some problems using loops would get really messy, really complicated, while using recursion makes it very clean. But there's also the other case where recursion would be very messy and loops would be very clean. And so sometimes you just pick and choose, but having both in your toolbox gives you a lot more flexibility and makes some problems a lot easier. So that's why we talk about it. So if we go back to the slides, we have kind of a picture of the structure of a recursive function. And this isn't exactly Python on here, but it's close enough. You can probably figure out what it's doing, even if we didn't learn this language specifically. But at the beginning, we just have our function definition, right? Here, we have a function called recursion. It takes in a single input. Right? And then in the screenshot, they use the curly braces to show the body. So inside this function, it does this if statement. I'm going to skip past that for now. The important thing, what makes this a recursive function, is this last line. If you notice, inside this function, it calls itself, right? It doesn't call itself exactly the same, right? This recursion is recursion x. This one is recursion x minus 1. So it's kind of like one less, but it's calling its own function, right? So a function is using itself, right? That's what makes it recursive. That's also what kind of gives you that loop idea where you're kind of repeating yourself in a good way. If we go back to the if statement now, this is where you have your base case. And so it's called the base case because that's kind of where you stop, right? If you imagine if you don't have a base case, what kind of problems can we run into? If we have a function that keeps calling itself, calling stuff, doesn't have a base case, well, you're going to get stuck in a situation where you kind of have an infinite loop. It's kind of like when we saw a while true loop, right? If you have a function that's just calling itself again and again and again and again, and you have no way of stopping it, well, that's not very useful, right? Because if you try to run it, then it's just going to run forever. And so the base case is what lets us stop this recursion, stop this looping idea. And so in this case, this isn't solving any specific problem, but it says if x is 0, I'm going to stop. If it's not 0, then I'm gonna call myself, but just with one less input. So if we go looking at the factorial example, so let's try to maybe come up with an idea of coding up a Python function to solve this factorial problem recursively. So I'm going to define the problem a little bit more rigorously. We want a function that takes in an input, we can call it x, and it wants to calculate x factorial. Right? And so the function, we have to say def. I'm going to call it the factorial function. And it's going to take in one input x. And so I want to put here the base case. So can anyone tell me what I should check for to see if I'm in the base case for this factorial function? So I'm going to leave a comment, base case. And yeah, earlier I said 1 is our base case because that's kind of where we know the answer immediately, right? If someone asks us what is 1 factorial, we don't have to think anything. It's just 1, right? And so we can just say if x equals 1, well, now we want to do something. Well, we can just return 1 because that's our answer. So I'm going to put an elif. You don't have to put the elif because if the first thing was run anyways, you wouldn't get to this part. So you don't need an elif, but I'm going to put it there to make it a little bit more clear what's going on. So elif, if x is not 1, how do we calculate x factorial? We kind of came up with a formula for calculating x factorial. Now we want to use it here. So elif, we want to calculate x factorial. And so remember, x is just like a random number. X could be 5, it could be 10, it could be 20, it could be 100. We can assume that people are only going to ask factorial of like valid inputs. So we can pretend that no one's going to put in a negative number, no one's going to put in a decimal value. We're always going to get nice inputs in this case. And so if we go back here, we came up with a formula for calculating the factorial, because if I write out what x factorial is, right? So what is x factorial? By definition, we start with x, we multiply it by x minus 1, we multiply that by x minus 2, we multiply that by so on until we get to like 3, 2, 1, right? We just go starting from x all the way down to 1, and we multiply it all together. And so we don't know what x is, so we can't really just give an answer immediately, but we have a way of figuring it out because we know x factorial is just going to be x times, what is this? This is just x minus 1 factorial, right? Because we have x minus 1 times x minus 2 times x minus 3 all the way down to 1, right? So we bring down the x, we have x minus 1 factorial. And so we have a formula, right? X factorial is just x times x minus 1 factorial. And we can see that x minus 1 factorial is a slightly easier problem to solve. But we're probably still going to apply the formula a bunch more times depending on what x actually is, right? So in the code, the result is going to be x times, well, how do we get x minus 1 factorial? This is where it gets a little bit tricky you have to remember we're writing the factorial function right now. And even though it's not complete right now, we can pretend it's complete and we can use the function that we're writing right now, right? We pretend that this factorial function is already completely finished, completely working as it should, and we just use it. And so we have this factorial function. And it's not going to be factorial x, it's x minus 1. Right? And we just return the result. And so this, hopefully, should give us a complete working function to calculate the factorial. Again, how it works is, first we check if x is 1. Because if it's 1, we don't need to do any work. It's just, our answer is already immediate. It's just 1. If it's not 1, we have to do a little bit more work. We have to use our formula that we came up with, which is just x times factorial x minus 1. And that's our result, right? And the trick is when we do this factorial x minus 1, we kind of repeat this whole body again for our new input. But that new input is going to be 1 less than before. And it's going to be 1 less, 1 less, 1 less. And eventually it's going to reach 1. And that's when we can solve everything. Right? And so if we run this cell, this again is just defining the function. It doesn't actually do anything. Oh, I had a syntax error. Let me check what's wrong here. It's a little bit embarrassing. Is it with my comments? Or what is wrong? Yep, so that's fine. Oh, my bad. I didn't want an elif here. I wanted an else because I didn't have a condition. It's just no matter what, if the first didn't run, I want an else. Sorry about that. So now it works. And we can test out our function. So if we just run it on a couple things that we already know to test it out, well, we can start simple. What is factorial 1? Make sure that this gives us 1, right? The most simplest one. And then we can work our way up. Factorial 2 should be 2. It is. Factorial 3 is 3 times 2 times 1 is 6. And it gives us 6. 4 factorial should be 24. 5 factorial should be 120. And it works. And so immediately now we can have factorials of a lot larger numbers. So factorial of 24 is this gigantic number. Factorials grow really, really fast. There is one downside of this though. If you try to do factorials of really large numbers, in this case it worked. It gives us this gigantic number. But eventually you get to the point where you can run into errors or just programs that take a really long time, right? And so this is kind of related to your question, Derek. What if we put a negative number? You'll actually see the same error here. And so this is another type of exception in Python, one that we haven't seen yet. This is called a recursion error. And if we just read the message, it says the maximum recursion depth exceeded in comparison. The whole message of this is basically just saying, hey, I have this recursive function. I'm calling myself over and over and over again. And notice, like, I don't, in this recursive function, you don't get your answer until you reach the bottom, right? Until you reach x equals 1, you're still just don't know what the answer is at all, right? Only when you get to, you're kind of building this stack of functions, just waiting for the answer, right? Because factorial x is waiting on factorial x minus 1. factorial x minus 1 is waiting on factorial x minus 2. They're all waiting on another call. And until you reach 1, x equals 1, you're just waiting, right? And so the program, the computer has to keep track of all these waiting functions. And your computer only has so much space. And if you have too many of these recursive functions just still waiting for an answer somewhere, you're going to run into this error called maximum recursion depth. Basically, the computer sets some sort of limit and says, hey, if I've reached this limit and I still don't have an answer, I'm just going to give up, right? I don't have more space. I can't do this anymore. I can't recurse anymore because I just don't have the space to store more information. So I'm going to stop. I'm going to give up. I'm going to throw an error. And so that's what we're seeing here. And this is the problem, sort of recursive functions. Recursive functions are inefficient in this way and a little bit slower in this way. And so that's why people don't necessarily love recursion by itself. There's things that you can help with recursion that makes it a lot faster, a lot more efficient. I'm not gonna get into that too much because it's a little bit beyond the scope of this class. But that I'm not trying to say recursion is bad. Recursion can be useful in certain cases. I'd say the factorial, even though we get this error for factorial 1000, is still a really great choice for this specific problem, just because the nature of the problem itself is just very recursive in nature. Like there's a very clear pattern. We didn't have to do any sort of manipulation to see the pattern. It was just there already, very clear. And it's very easy to apply this recursive function. We could come up with a loop version of this code. In the interest of time, I'm not going to do it here, but we're going to see an example later on today. Yeah, so in the slides, I have another example of a recursive function. It's very similar to the factorial. So this example is coming up with a function that adds up all positive integers from 1 to a given number. So instead of multiplying, which is the factorial, this is just adding it up. And if you imagine the code is going to look almost identical. The only difference is instead of doing x times factorial x minus 1, you're going to do x plus whatever your function is, x minus 1. And so if we look at the code, our base case is still the same. If x is 1, we're done, right? Return 1. Otherwise, if it's not 1, then we're going to return x plus all the numbers up to x minus 1, right? 1 less than it. So that's just another example of a recursive function. And here is an example of loops and recursion. So here, we're getting to the Fibonacci sequence. So just so everyone's on the same track, let me make sure everyone knows what the Fibonacci sequence is. So typically it's going to start with like 1, 1. That's, I think, the most common. And it's just a sequence of numbers, a list of numbers. So to figure out the next Fibonacci sequence, Fibonacci number, you just add up the previous 2 numbers. So here, the previous 2 numbers are 1 and 1. So if you add them up, you get 2. Now to get the next number, you take the previous 2. Now it's 1 and 2. You add them up, you get 3. The next number is 2 plus 3. It's 5. The next number is 3 plus 5. It's 8. And you can see it's getting larger and larger. It's going to be 13, 21, 35. And I don't have to write all these down. I think I might have messed up my, math there, because I know 9. I'm messing up my math. I'm gonna stop embarrassing myself. Yeah, but one test I'm gonna use to make sure it works is I know the 12th Fibonacci number is 144. No. Make sure. Did I do this correctly? This should be a 34. That's why it messed up a little bit weirdly. It should be a 34 and 55 and then 89. And then you get 144. Yep. All right, so this is the Fibonacci sequence. Basically just, if you want to figure out any Fibonacci number, it's just the previous two added up, right? That's how you get the Fibonacci sequence. And it's an important sequence in math. There's a lot of different places where it pops up. But in our case, we're just interested in calculating these numbers. And so you can very, very easily do this with a loop, right? The sum of any two elements defines the next one. So in our loop, we can just calculate this by just keeping track of the previous two, adding it up, getting the next one, adding up the previous two, getting the next one. And so here is printing out the first 10 Fibonacci numbers. Basically, we're starting with 0 and 1 instead of 1 and 1. That's another way of starting the sequence. It doesn't really matter because if you start with 0 and 1, if you start with 0 first, then the next number is just 0 plus 1, it's 1, and then you're back to the normal sequence. I personally like it starting at 1, 1, but minor difference. So here, while b is less than 10, we're just printing out all the numbers less than 10. In this case, we print out b, and here's a new syntax that we haven't seen before. It's a little bit weird, but it's just like a shortcut that we can do in Python. It basically allows us to assign two values to two variables at the same time. And the reason why this is necessary is because we want b, like a plus b, and we want to store that into b, because a and b store the previous two numbers, right? And so we want to update them. And one of them should become a plus b, the sum of the previous two. But if we update one of our variables with that, and then it's already updated, we have trouble updating the other one. And so this just allows us to do all the updates at the same time. A becomes b, b becomes a plus b, and we just repeat in a loop. And we stop when b is greater than or equal to 10. Okay, so this will print out 1, 1, 2, 3, 5, 8. Right? Because once it gets to 13, it's greater than 10, it doesn't print it. We can do this, though, with recursion. And the reason why this is an interesting problem with recursion, a little bit more interesting than the previous example, factorial, is because here now we have kind of multiple base cases. And also, we're not just recursing once every time, we're recursing twice every time. Because if we look again at kind of the structure of this problem, we can draw it out kind of using a tree. So to calculate, I'm going to call my function fib. So to calculate Fibonacci, the fourth Fibonacci number, right? What is this? We don't know, but we have a formula for it, right? It's just going to be fib 3, or let me draw it, fib 2 plus fib 3, right? The fourth Fibonacci number is just the sum of the previous two. And so this one function calls itself twice. Each of these call itself twice again. Well, actually, not exactly, because we have a base case here. I'll talk about why in a second. But we actually have two base cases here. Our two base cases are, I'm going to use 1, 1, right? Because to start off the Fibonacci sequence, you have to know your two starting numbers. And so since we have two starting numbers, we have two base cases. Fib1 and Fib2 are both base cases. So if someone asks us, what is Fib1? We say 1. What is Fib2? It's 1, right? For any other Fibonacci number, we're going to calculate it using our formula, right? And so here's the picture of calculating Fib4. It's going to be Fib2 plus Fib3. Fib2 is a base case, so we don't need to do anything more. Fib3 is not a base case yet, so we have to recurse. It's Fib1 plus Fib2. Right? And so this is the tree for drawing Fib4. If we wanted to calculate Fib5, notice I'm going to move everything up a little bit so we have room. And I'm going to maybe move this all the way to the top and zoom back in. So if we wanted to do Fib5, there's a little bit of more work. So Fib5 up here. Fib5 is, or actually I'm going to draw it the other way. Fib5 is Fib3 plus Fib4, right? And then Fib3, again, using our same formula, is Fib2 plus Fib1. Right. And so this is our tree for Fib5. You can imagine our tree for Fib6. It'd kind of be almost two copies of this. Almost, but not exactly. And here again is where I want to point out some of the inefficiencies of this recursive definition for Fibonacci. So again, why do we use recursion? It makes the problem very simple because the sequence itself is defined recursively. So since it's a recursive definition, of course, a recursive function is going to be very easy to apply. On the other hand, the simplicity comes with the cost. It comes with the cost of performance. Because the reason why I drew out this tree is, if you notice, you're kind of, even to calculate Fib5, you're kind of repeating work here. Because if you look at the tree, well, how many times do we compute Fib3, right? We compute it once here, but we also compute it once here. So we compute it a total of 2 times. And if we look at how many times we compute Fib2, well, it shows up once here, shows up once there, shows up once there. We have to do it 3 times for the same number, right? Fib2 never changes. It's always the same number. But in this tree, we had to calculate it in 3 different places. And so that's a little bit inefficient. Some of the ways that you can improve this is to basically store the results along the way. And so in the future, if you ever need to calculate Fib4, well, you've already solved it. Because when you're calculating Fib5, you had to figure out what Fib4 was. You had no choice. You had to figure it out. And so later on, if someone cares about Fib4, you don't need to do the whole calculation again. You already have it. And so that's not something I'm going to get into more than that. That's just an idea of one way you can improve recursive functions. But if we go and program this, I'm going to call it fibrec for recursive, and it takes in a single number. I'm going to call it x again. And again, we have to check for our base cases. So I'm going to write it as if x is less than or equal to 2, because we know 1 and 2. If x is less than 2, we just return 1, because that's what it is. The first number is 1, the second number is 1. Else, now we need to use our formula. We want to return our recursive formula for calculating x minus 2 and x minus 1. Right, so the xth Fibonacci number is just x minus 2 plus x minus 1, or Fibonacci x minus 2, Fibonacci x minus 1. And so this is our definition by itself. And we can try it out. So let's just call it on a couple of different numbers. Not next year. So maybe the third Fibonacci number. If we look at our sequence, this should be 2, and we get 2. If we do 4, we get 3. And like I said before, the 12th Fibonacci number should be 144, and it is. So it works how we want it to. Later on here, I do have this is a different function, but so this is our recursive definition, and I'm going to do our iterative. So our iterative solution, we just need to keep track of our first 2 numbers and keep adding it up, keep calculating the next number again and again. So we can start with 1, 1 and work our way up. So I'm going to use AB. So A equals 1, B equals 1. And then we can just repeat this calculation essentially X times. You have to be a little bit careful with how many times you repeat it. You can also have a similar base case. Like you can also check if X is less than 2. Because again, you don't need to do any work if it's less than 2. But if it is, then you want to do like a loop. And so I can just say for, I don't know, I in range, I think it's going to be X minus 2. I'm going to use a shortcut. So A becomes B and B becomes A plus B. Right. And at the end, if I do this correctly, I'm going to return B, and hopefully that should give us the answer. So if it is, it might be 1 off or something like that. Hopefully it's not. I didn't want the underscore. Oh, okay. So I did it right. So the iterative solution also gives us 12. And so you notice I'm going to actually put this in the same. Now we can compare. I'm going to put the iterative solution. So we can have kind of like a race, right? So if the input is 10, right? Or our variable is 10, I'm going to calculate the ith Fibonacci number both ways, iteratively and recursively. For something like 10, they both run pretty much instantly. Neither one has any sort of issues calculating the 10th Fibonacci number. And so if we do this, both of them say 55, this is great. Go to 20, still pretty much immediate. 30, immediate. But at some point you're gonna see, notice we're getting a delay at this point. And notice the iterative solution gave us a solution pretty much immediately. But this recursive one is taking a lot of time. And in fact, this might actually take multiple hours, might take longer than any reasonable amount of time. So this one took like 2 minutes, but if we go to 50, I can pretty much guarantee that this is not going to finish within a week, even if I let my computer just sit here and calculate, it's not going to finish. But yeah, so the trade-off here, again, if we compare this, recursive formula, a lot shorter, a lot simpler than this iterative solution. And so that's kind of why we like recursion. It makes problems easier. In some cases, recursion makes it like almost trivial. Well, if you try to do it with loops, it's like really, really difficult. In theory, they can do the same things. Anything you can do with loops, you can do with recursion. Anything you can do with recursion, you can do with loops, in theory. In practice, it's not always really practical to do a problem, solve a problem in a certain way. And that's why you want both. So that's really the important thing for today's class. Just introducing recursive functions. After today's class, getting a little bit ahead of myself, but we're gonna begin talking about something called classes in Python. And because of that, we're not gonna talk about functions specifically anymore. Again, we're just like building upon our knowledge a little bit more and more. Classes you're gonna see are gonna contain functions inside of them. So we've kind of like been growing bigger and bigger. In Python 1, we just learned different commands, different Python statements that you can do. Then we learned loops that can repeat those statements again and again. We also learned definition functions now, where you can combine a bunch of code inside a single package. And now we're going to see classes, which basically combine a bunch of functions into a single package. We're just growing bigger and bigger. So because of that, this is it for our discussion of functions specifically. If you have any questions, though, I'd be happy to answer them now, happy to answer them on Classroom as well. In terms of homework, I don't have something planned yet, but I will be posting a homework for today's class, probably a very similar recursive problem to either Fibonacci or the factorial, just something to practice if you have the chance. Just a reminder for next week and the week after, it's going to be Christmas and New Year, so we're not going to have class. But starting on the 8th, I believe, we're going to go back to our normal class time, Saturday, 3 to 4. So today it was a little bit weird. Sorry about that. We're going to go back to our normal time starting next year. I think that's pretty much all I had to cover. Luckily, today was a shorter class in terms of material anyways. Yeah, if you have any questions, I'll be sticking around. If you don't, that's all I have. Have a great holidays, have a great Christmas, have a great year, and I'll see you on the 8th.
Bye.
Bye, Derek. You too. Oh, sure. Code to the question, yeah. Let me pull that up. So here's the code. I can paste it into chat. Yeah, no problem. Yeah, I'll post sometimes the code that we work on. I'll post the homework. And you can, if you have any questions later, you can leave a comment and I check on that every now and then. Yeah, thank you. You too.